This is a mini ITX motherboard that is designed specifically to use for NAS. Now you're probably familiar with this type of layout on an ITX motherboard, which comes usually with some sort of socketed CPU, one or two full-size RAM slots, two, if you're lucky, maybe 4 SATA slots, and then a full-size PCIe slot. And clearly you've got usually some USB display out and some sort of Ethernet connection here. And in this case, this has an M.2 slot and a Wi-Fi slot as well. So if you're building something like this basic 4-bay NAS box, something like this would probably be more than sufficient for that use case. However, if you're looking to build something like in this Johnsbo N3, which can support up to 8 hard drives, you're going to need something with a little bit more expansion options, more than likely. That's where a device like this comes in. Now, it isn't made by any known manufacturer like Asus, Gigabyte, MSI, or ASRock. I did get this from Amazon. You can also find it on AliExpress, probably cheaper, but they're pretty much a no-name brand, but they do come with some quality components. Now, this is an N100 Alder Lake 6-watt TDP, 4-core, 4-thread, 3.4 GHz CPU that supports up to 9 PCIe lanes. They also have a version which is based on the Jasper Lake Celeron N5105, which is also a 4-core, 4-thread, but a 10-watt TDP CPU, and it supports up to 8 PCIe lanes. Once I get these all hooked up, I'm going to install and perform some benchmarking on Windows 11, Ubuntu, TrueNAS Scale, Unraid, and Open Media Vault. But first, let's take a look at the components that are on each of these boards. As you notice, it has a heatsink and fan here, which comes with the board itself because the CPU is actually soldered on. Again, it's a Celeron N100. It also supports a single channel DDR4 or DDR5 RAM chip. This particular board comes with a DDR5 socket, and it uses the traditional laptop SODIMM type RAM here. And the specs for the CPU do call it up to 16 gigabytes. I do not have a 32 gigabyte chip, otherwise I'd check to see if it'll actually support more, but it should support the 16 gigabytes there natively. You notice it also has a 24-pin ATX connector here, as well as a 4-pin CPU connector, so a traditional ATX power supply will work with this board. You can see the onboard USB 2.0 port, and then I flip the board around here, and you can see that there are two M.2 slots here. They're supposed to be NVMe and PCIe 3.0 standard, and my assumption is that they're PCIe 1x lane each because of the limited number of lanes supported by the CPU. Now if you look down here, you can see that we have a PCIe 1x slot. If you are not aware of how PCIe works, the front section here up to that divider there supplies the power to the device up to 75 watts off the motherboard. Then anything beyond that is just the PCIe channels. And you look on a traditional 16x slot here, obviously it goes all the way back here, but in this case it's just that little segment there. The nice thing is that the back end is open so that you can slot in a larger than a 1x card in here without having to use an adapter or make any modifications to the board. We'll take a look at that in a second. So that's actually nice to have. Even though you only get the 1x speed, you do have expansion options there. Now moving to the back over here, you can see that there are 6 SATA ports here, and if you look closely you can see the J-Micron JMB 585 chip, and that supports up to 5 6 gigabit or SATA 3 ports. So 1 or 2 of these are probably taken off the CPU, as I believe the CPU itself can support up to 2 SATA ports natively. So it's using 4 or 5 off of here and 1 or 2 off of the CPU. Now moving on to the back ports, you've got 2 USB 2.0 ports, a full-size display port, full-size HDMI, 2 USB 3 ports, which should be 10 gigabit. But what I like most about this board is that it supports up to 4 2.5 gigabit Ethernet ports. And it uses the Intel i226V chipset. And if you know how to do link aggregation or SMB multi-channel, you can link them all together up to 10 gigabit of total speed, or you can use them as independent networks or failover or whatever you want to. And looking at the bottom, there's really not much there other than the 4 screws that support the CPU heatsink and fan. Now I propped this board up on a box because I want to show you this PCIe 1x slot and slotted in a couple adapters. In this case, this is a PCIe 8x card. And you can see here it fits in there just fine. The problem is that it overhangs the SATA ports. And not a huge deal because you could just use right angle SATA cables if you needed to. However, if you happen to use a 16x card, like this guy here, this video card, it's going to slot in between the SATA connectors there. So thankfully it does slot in there. The problem is that if you happen to have even right angle connected SATA cables, the clips on the back are going to interfere with the board itself, so it'll make it difficult to slot it in there. So I have these right angle SATA connectors or cables with the clasp on it. So if I snap those in here, okay, those are now in place, and you can see that the latch here overhangs that gap there where the PCIe card wants to sit. So you really need to go with something more like this guy here, a right angle without any kind of clasp on it. And that should give you the clearance you need to put a PCIe card in there. So I have one of these right angle connectors in here without the clasp on it, and you can see that there's plenty of clearance here to put the PCIe card. And on the other side, these three SATA connectors, you can use regular straight out SATA connectors even with the clasps because it's not going to interfere. So if you take this 16x video card, it'll slot in there just fine. Now taking a look at the N5105 version, again you've got the Celeron N5105 Jasper Lake CPU, which is 4-core, 4-thread, 10-watt TDP, and it supports up to 8 PCIe lanes. And if you notice, what is absent from here is a actual PCIe 1X slot. So that's probably because it only supports 8 PCIe lanes and not 9 like the N100. Now notice it has 2 SODIMM slots, so it uses traditional DDR4 laptop type SODIMM RAMs, and up to 16 gigabytes total. And I did put a 16 gigabyte RAM in here. It did not boot. I put 2 8 gigabytes and it booted just fine, and a single 8 gigabyte booted just fine in this guy here. And it also uses the ATX 24-pin power connector, and the 4-pin CPU connector is over here. This also supports 2 M.2 slots, which you can see they're oriented a little bit differently than the N100. This one runs perpendicular to the CPU, whereas this heatsink, whereas this one runs parallel to the heatsink here. And they're both, again, supposed to be M.2 NVMe, and we'll take a look at that closer. I thought I would also mention that both of these boards and the M.2 slots, they only support the 2280 form factor, the 80mm long form factor. So if you want to use a 2260 or 2242 SSD, you'd have to get some sort of adapter for that. And you can see it also supports the 5 SATA ports here, and it also has, I did pull this heatsink off, and it does have a GMB 585 chipset on here as well. Looking at the back, you've also got the USB 2.0, full-size display port, HDMI port, 2 USB 3 ports, and the 4 2.5 gigabit Ethernet jacks that are also the Intel i226V chipset. And you'll notice that this has 2 onboard USB 2 ports. And again, on the bottom, same thing like the other one, there's really nothing there, just the 4 screws for the heatsink for the CPU. Now you may be wondering, okay, I've got 6 SATA ports on here, but what if I do have something like this Johnsbo N3, which supports up to 8 SATA hard drives? How do I get my other 2 SATA hard drives connected to this motherboard? And you could probably do this on a traditional ITX motherboard, but because you have the 2.5 gigabit Ethernet ports on here, it does give you expansion options because you don't have to use up your PCIe slot for a faster network adapter. Now you could use something like this M.2 Orico. It uses an Asmedia controller which supports up to 6 SATA ports, the full SATA 3 or 6 gigabit SATA ports. Or you could use something like this SAS adapter, which uses these connectors, and you could use a connector that has this on it with 4 SATA connectors on the other side, so you could support up to 8 for this guy here. Or in the case of this N100 board, you can just get a traditional SATA card that you could just slot in here like this and connect your SATA ports that way. Now, full disclosure here, I did get this N100 board that I was using initially, and it did end up having some issues where an Ethernet port ended up just disappearing, not sure why, and it did end up starting to hang and lock up. So I did request for an RMA. They shipped me out a replacement board right away. Another thing you'll notice here is that the SATA chipset doesn't have a heatsink on it, whereas on over here it does. Not a huge deal. Sometimes I probably make decisions later on that they don't need it, but either way, I'm wondering if maybe this was a return or something. But the new board seems to be working perfectly well, knock on wood. So this is what the benchmarks are all based on, is a new board. Now you may be wondering why this motherboard and not just use a traditional ITX form factor motherboard. Finding an ITX motherboard that supports at least one 2.5 gigabit Ethernet port and has at least a second M.2 slot so you can do some expansion can actually be difficult to find and also get expensive really fast. And you're looking at typically at least $200 just for the motherboard, and then adding in a CPU on top of that. And so it can get expensive real quickly, and you don't always even get all the features that you need. Now there are other ITX NAS-based motherboards out there, like the CWWK, which is an AMD chipset, and it comes with a full-size 16x PCIe slot, and the M.2 slots are actually full 2x lanes, and you can support up to, it says, 9 SATA ports through these connectors here, and it also has 2.5 gigabit Ethernet, etc. However, you look at the cost, I mean, you're looking at $423.17 for this guy compared to the $125 for the board that we're looking at. ASRock Rack also makes some nice server-based motherboards or NAS-based motherboards, but again, these are difficult to find, and when you do find them, again, they're expensive. They're $400 to $600 a piece. So this is my setup here. I've got two sets of 6 500 gigabyte 7200 RPM hard drives, and I'm going to use those to test both the SATA ports and the throughput there, as well as using the M.2 adapter to 6 SATA ports here through an M.2 slot on each of these boards. And I've got M.2 PCIe SSDs for the boot drive, and then 8 gigs and dual channel 16 gigs and dual channel 2 8 gig chips on the N5105 board, and then a single 16 gigabyte chip on the N100 board. And I've got the EVGA 500 gold power supply, and also going to be measuring power through the device over here. For testing the M.2 slots and the throughput in the USB ports and the PCIe 1X slot, I needed a couple of fast NVMe M.2 drives, and that's where these come in. This is the Samsung 970 EVO Plus 2TB and the WD Black SN770 2TB M.2 NVMe SSDs. Now I also have this 16x PCIe slot adapter for NVMe drives, so I can test the PCIe 1X slot, but I also stuck this in my desktop, the 16x slot in my desktop, to get a baseline for the performance for these disks, and I'll show you the Crystal Disk Mark results here. So you can see that it's plenty fast to support up to a 4x slot, and these devices are more than likely only a 1x PCIe anyhow. When it came to installing the operating systems, there were really no issues with the Linux-based ones, Ubuntu, OpenMediaVault, TrueNAS Scale, or Unraid. After an installation and update, all the devices were detected and working just fine. But Windows 11, on the other hand, had some missing device drivers that I had to hunt down because there is no support site. I did email the vendor, and they just said they're on the internet, so a lot of use that was. Most importantly, though, the Intel i226V Ethernet controller was not detected, which is the chip that's used on both motherboards. So I had to locate and download the drivers from another PC and load them in through a USB drive before I could even update Windows, because I had no network connection whatsoever until I got those drivers installed. Once I got them installed, after Windows Update completed, there were still a couple missing devices. For the N5105, I found some chipset drivers on Gigabyte's website, and that cleared those up. For the N100, there was an SM audio bus device that needed updating, and after some scouring, found some drivers through Microsoft's driver catalog website, and another driver from someone at 10 forums through a Google Drive download. So that, of course, made me a little bit skeptical, but I did scan it, and it did come out clean for viruses, no viruses, and in the end, everything worked fine. I ran a lot of benchmarks on each of the system components on both motherboards. For the CPU RAM, both M.2 slots, the PCIe 1X slot that's only on the N100, the four 2.5 gigabit Ethernet ports, the 2 USB 3 Type A ports, and the 6 onboard SATA ports. I mainly checked for functionality and general performance on the 5 operating systems that I installed on here. First up, the M.2 ports and the PCIe 1X slot on the N100 are definitely only 1X PCIe 3.0 lane, as they benched only about 850 megabytes per second sequential performance in Crystal Disk Mark, KDisk Mark, and the HD Prime-T tests. And then when doing an actual 1 gigabyte file transfer test, it ran about 800 megabytes per second. For reference, the theoretical maximum for PCIe 3.0 1X lane is about 1000 megabytes per second. The 2 USB 3 Type A ports on the back performed even better than the M.2 slots, actually, hitting about 1000 megabytes per second with the Crystal Disk Mark and HD Prime tests. The real-world 1 GB file transfer tests were all over the place, though, but the N100 typically fared better than the N5105 in that situation. For the 2.5 gigabit Ethernet ports, they were all instantly detected at 2500 megabit per second link speed. And when performing a 10 by 1 gigabyte file transfer over the network, they all ended up about 270 to 280 megabytes per second, which is where it should be. The only exception was the N5105 Windows write test, where it only performed at 240 megabytes per second, but read performance were all similar in performing at expected speeds. I can't explain the Windows reason, it's probably just Windows being Windows. Looking at the SATA ports, which is important for setting up a NAS, right? The 6 SATA ports on board had some interesting, if not confusing, results. I did run through a number of tests, including single disk, 6 disk grade 0, 12 disk grade 0, 6 disk grade 6, and 2 6 disk grade 6 arrays and RAID 60 setup. And without getting into too much detail, the bottom line is that the N100 SATA ports restrict performance for some reason. Connecting a fast SSD to each SATA port individually, the individual port performance was limited to about 420 megabytes per second, which you can see here. This indicates each of these ports, and this is the speed, average speed over that port, comparatively with the desktop PC that you can see here, where the same SSD was plugged in, which ran closer to about 560 megabytes per second. The weird thing is, you notice that this port 2 actually runs faster than the other ports. My thought is that this port actually is connected directly to the CPU, whereas all these other 5 are connected to the JMD 585 Micron chipset. So 420 megabytes per second should be perfectly fine for a single disk situation, right? Because hard drives typically don't run faster than 200 to 250 megabytes per second individually anyhow. But if you are running SSDs, obviously you're going to hit that wall and become a bottleneck. However, more concerning is that when connecting 6 hard drives in a RAID 0 array, it actually peaked at about 500 megabytes per second for the array using the onboard SATA ports on the N100, whereas the N5105 and the Orico M.2 adapter offered out over 900 megabytes per second. It just is odd because the N100 and N5105 SATA ports both use the same Micron JMB 585 chipset. To test a real-world scenario, you look at the 1 gigabyte file copy. You can see here that the N5105 and the Orico really didn't fare much better than the N100 anyways in the real-world file copy test, so maybe it's not as big of a deal. Okay, now I'm going to show you the limits of the onboard SATA port here. This is the N100. Here's the 6 hard disks that are connected to the 6 SATA ports on board, and I've got it running in Open Media Vault here. So here you can see the 6 disks, SDA through SDF, which are the 500 gigabyte, 7200 RPM hard drives that I just showed you. And it did do a quick HD PARM test on each of those, 206 megabytes per second, all the way down to 186 megabytes per second, but around 200 megabytes per second on average. Now I'm going to go ahead and build a RAID 0 array. Here you can see I have the RAID 0 array created, and I did a cat proc md stat, so you can see here's the RAID 0, and then I'm going to go ahead and do a HD PARM. End up with about 515 megabytes per second. Now I'm going to do a timed copy of the 10 1 gigabyte files from the Samsung SSD over this USB adapter over to the RAID 0 array. And you can see here that it equated to 16.626 seconds. So if you take the total of those file sizes, 10,240 megabytes, divided by 16.626, gives you 616 megabytes per second. Now why it's higher is probably because it's been cached through RAM. So the first few gigabytes will be cached through RAM, so it'll be faster. So now I'm going to shut down, and then I'm going to switch the disks over to the Orico M.2 array. Okay, so now I have the 6 hard drives connected over to this Orico M.2 add-in card. I'm going to go ahead and run the same tests that I did on with the onboard SATA ports. Well, first up, we're going to go ahead and do the HD PARM. There you can see we have a 835 megabyte per second transfer speed as opposed to 515 megabyte per second transfer speed we had previously. Now I'm going to do the file copy test. This time it took 14.138 seconds. So that's about 724 megabytes per second. Okay, so here are the 6 hard drives again, but this time connected to the N5105 and the onboard SATA ports. I'm going to do the same tests over here. So we'll do a cat proc md stat, and it is now named MD127. So instantly you can see there we have 1000 or 1 gigabyte per second writes to the same RAID array, but on the N5105. And if I do the file copy test, and there we have 14 seconds. So again, 10240, 727 megabytes per second. You can see I've got the N100 version of the motherboard here, and I've got 12 hard drives hooked up to it, with 6 of them going to the onboard SATA ports, and then the other one to the Orico 6-bay with the Asmedia 1166 chipset on it. And I'm going to set this up in a RAID 60, and you can also see that all 12 disks are detected here in Open Media Vault. So the first thing I want to do here is just select this, do RAID 6, and select the first 6 disks. The other ones are down here. Now I'm going to go ahead and click Save, and it's going to start to make that. But before I approve this, I'm going to go ahead and make another RAID 6 and go the additional 6 drives. Click Save. And then I'm going to go ahead and apply this. I'm going to generate these arrays at the same time. Now if you notice, MD0 are the onboard SATA ports and MD1 are the Orico. You can already see that the Orico is building a lot faster than the onboard because of that 500 megabyte per second limit it seems to impose for some reason on those SATA ports. Now here you can see, first I did a single disk RAID 6 build on both the N100, which is blue, and the N5105, which is pink and purple, and the N5105 took 106 minutes, whereas the N100 took 127 minutes. Now when I built both of these RAID 6s simultaneously, the N5105 still completed both RAIDs at the same time in 106 minutes, and the N100, the onboard SATA ports, took 145 minutes, and the Orico M.2 adapter actually finished in 114 minutes. So it seems like that SATA port is definitely restricting performance during a RAID 6 build as well. I also tracked the CPU usage while the RAID arrays were being built, and you can see that the CPU utilization was at about 50% with the N100, with the load average of 15 minutes at around 4. So it was pretty much heavily loaded. And then you look at the N5105, it also was about 50% CPU utilization with a load average, hit up at about above 4, and then actually peaked all the way up to about 4.5. However, system responsiveness was actually pretty decent. I set up Unraid with a 4 data disk and 2 parity disk scenario using the 500 gigabyte hard drives, and I did the initial sync, and both with the onboard SATA ports and the Orico M.2 SATA adapter. And you can see here that the N5105 took 53 minutes to complete. The Orico on both N100 and N5105 took 53 minutes to complete, but the N100 onboard took 77 minutes. Now once I created that initial sync, I went and did a parity check, and as expected, the parity check should take about as long as initial sync, and it took 54 minutes on the N5105 as well as the Orico on the N5105, but on the N100, it took 93 minutes to finish that on the onboard SATA, and the Orico took 60 minutes. Not sure why it took a little bit longer in this case, but those are the results. For TrueNAS Scale, I set up a 6-disk RAID Z2 array, which is effectively a RAID 6 or 4 data 2 parity disk scenario, however you want to look at it. And it did a file transfer of 1 terabyte of data over the 2.5 gigabit Ethernet network. And you can see the results here. I didn't expect these to be too far off from each other because you only talk about 200-something megabytes per second, and those are the results. Now, once I got the data there, I did pull a disk and then replaced it, and then did a resilver of the data, and the N100 with the Orico M.2 adapter and then 5105 both took 38 minutes to rebuild, and then the N100 with the onboard SATA adapter took 47 minutes to rebuild. So you can see, again, the onboard SATA ports are affecting the performance of the disks. Speaking of system performance, I ran Cinebench R23 before and after I did a repaste. So I removed the heatsink and fan, removed the thermal paste that was on there, cleaned it up, and put a better thermal paste on there, just see if I could get any improvement in temperatures or performance or anything. So here we have the N100, and what's important here is that you can see that before and after the repaste, the legend is down here, the CPU utilization didn't really change. This little dip here is indicated because at the end of the R23 scene rendering, it will reset, and so it can sometimes the CPU utilization will just drop quickly and then spike back up when it starts up again.
In any case, the clock speeds didn't change, and the CPU power difference really wasn't much different. The numbers here just represent the peak of each of these graphs after the 90-second initial boost speed. So right here it indicates 80 Celsius, which was the peak, but the average throughout this test was about 74, 75 Celsius prior to the repaste. Then after the repaste, it averaged about 55, 56 Celsius. So you're looking at about a 20 Celsius drop in temperature overall. As far as the N5105, you can see here we ended up with about a 10C or 12C drop on average. So not quite as drastic, but still an improvement. And everything else, all the other metrics didn't really change much though, so it didn't really affect performance so much. The next benchmark is using Handbrake to encode a 4K 60 10-minute long video to 1080p 30 frames per second using the default fast 1080p setting in Handbrake. And you can see the results here using QSV as well as CPU. QSV is the quick sync video or the embedded GPU acceleration for encoding videos. And you can look here, the N5105 took about 39 minutes to encode the 10-minute video and 28.6 minutes for the N100. Compare that with the i3-10105, about 16.5. And using quick sync, you improved on that slightly. So you can see it's not a real powerhouse when it comes to encoding. Speaking of encoding, if you want to use this for a Plex media server, it's okay to serve up 2, 3, even 4 files simultaneously as long as they're in the native format and resolution. Didn't seem to have a problem with that. But when it came to transcoding on the fly, there's no way it could handle. I tried a single 4K 60 video, converting it to a 1080p, and it just would buffer and pause and stutter and stop for a good minute or two before it could even pick up again. So that's not a possibility. But as far as serving just regular video files, it's not a problem at all. Now I also checked power usage in an idle and a loaded scenario. In both versions of the motherboard, idled at about 20 watts when configured with the onboard CPU, 16 gigabytes of RAM, single M.2 NVMe drive, a single Ethernet port connected, and then using a 500 watt EVGA Gold PSU. And at load, the N100 would typically run 35 to 40 watts, whereas the N5105 would peak at about 30 watts. So in the end, what does this all mean? If you're looking for a budget build primarily for storing and serving files, either option seems to check all the boxes. As I was able to successfully connect up to 12 disks with the use of an add-in card without issue. In both versions, you get a low-voltage 4-core, 4-thread Intel CPU, 4 2.5 gigabit Ethernet ports, 2 M.2 slots, 2 10 gigabit USB ports, and 6 SATA slots. And in the case of the N100, you also get a 1x PCIe 3.0 slot. In both cases, the CPU is more than adequate for managing software RAID configurations, including a 12-disk RAID 60 with MDadmin and Ubuntu and Open Media Vault, as well as a VDEV comprised of 2 6-disk RAID Z2 arrays in TrueNAS Scale. Although with a maximum RAM support of only 16 gigabytes, it might become a limiting factor, especially with TrueNAS, depending on what features you enable. I'm mostly excited about this board only because there are, unfortunately, not a lot of full-featured NAS boards using the ITX form factor. And the ones you can find are usually quite a bit more expensive. Since they are a generic brand, don't expect any support or warranty with these boards though, so you kind of have to take a leap of faith with it. But at $125, it's affordable, makes use of known name brand components like the Intel CPU, J-Micron SATA controller, and the Intel i226V 2.5 gigabit Ethernet controller. And for my testing, other than the N100 board that I had to have exchanged when I got the replacement, they both handled their workload without any other issues. The biggest concern was with the N100's onboard SATA ports that were underperforming for some reason, despite using the same J-Micron JM585 controller chip as the N5105. It worked, it seemed to gimp performance a bit in most scenarios. I mean, maybe it was just this particular board maker that has issues, as there are others available on AliExpress. Otherwise, the N100 does offer the added benefit of a PCIe slot if that's important to you. I actually plan on making use of the N5105 version of this motherboard in a home NAS project I'm working on, so hopefully it can provide some long-term feedback down the road. I guess that means I should tell you to like and subscribe if you want to get notification of such a video in the future. I hope you found this helpful. Until next time, talk to you later.